We shall continue our study of programming in C, and we shall pick up from where we left off in the last class. In the last class we were discussing functions, and C allows the definition of a large number of variety of functions, but the format in which functions are called is very simple. A function, there are no individual items like subroutines and functions. There is no difference between a subroutine and a function in C. Everything is a function, and you have the actual arguments of the function and the formal parameters in the function declaration. And as we mentioned previously, the calling is call by value. In call by value, the idea can be understood by the following scheme, that whenever a function is called, the values of the formal of the actual parameters are copied into the instantiated values as instantiated values of the formal parameters in the called function. That is, these form local variables of the new function, and the values of the main program from where it is called, or any other function from where it may be called, are copied here and executed, and after the execution they are not copied back. Therefore, whatever you call it with, the actual values of these variables will not change. And we understood in the previous class that if we require to change the contents of m and n, we would actually have to pass the addresses, and once we pass the addresses, we would have to change the contents specifically from the addresses. So we'll pick up from there, and we'll see another example and then move on to something else. So let's go back and watch an example of an exchange program. Now this is a program. We have got the main function here up to here, and in the main function we declare two variables a and b, which are integers, and then we read them, and before the function is called we print the values of a and b. We call exchange 1 ab, this is exch1 ab, and after the call of this we again print the values of a and b. Here we are passing the actual values, and here in exch2 ab we pass the addresses of a and b by saying and a and and b, and after this call we return, and in both we attempt to swap. So in the first one, exch ij, the actual values are passed, and we do a swap like this. Therefore, since a and b are integers in the call exch1, here in exch1 I and j are also integers, and we do a simple exchange here. Whereas in exch2 we pass the addresses of a and b, and therefore we declare I and j here to be pointers or address locations, in the sense that the content of I is an integer and the content of j is an integer. Star, as we mentioned before, is the content of a variable. Sometimes they are also called addresses, sometimes they are also called pointers. In C, the language often used is pointers, and we shall slowly adjust to this language as we move through the course. But it is always easy to understand the meaning of variable declaration this way. This says that the star I, which means the content of I, is of type integer. And here we specifically change the contents because we've got only the addresses or the pointers to the location. So we do a swap. Temp is equal to content of I, content of I is equal to content of j, and content of j is equal to temp. And as it is a call by value, what do we expect here? Whatever we got for a and b, after the call the values of a and b will not change. On the other hand, here since we are passing the addresses and we are doing an exchange, the value of a and b should change here. So just we will execute it and see how it works. So if we pass 3 and 5, after the first call we get back 3 and 5, and after the second call we get back 5 and 3. This does not mean that the exchange did not take place here. If we want to see whether the exchange really took place here, we will just see what happened here, and that will help us to understand that whether the exchange actually took place. So inside the first call we will print the values of I and j. If we print the values of I and j inside the first call, we should be sure whether the values exchanges actually took place or not, and we will see that the exchange actually does take place. You see here, before the first call it is this, inside the first call exchange takes place, but after the first call again the values of A and B remains the same. This is due to the fact that the call is call by reference, call by value, sorry, it's not call by reference, it's call by value. Therefore, even though the exchange takes place here, the values of A and B do not affect the I and J do not affect the values of A and B. On the other hand, if you pass the addresses and change the contents of the location, the values of the addresses do not change, but the contents have changed. Therefore, even though it's a call by value, by passing address locations and changing the contents, we can make modifications in the fields. And this is how we do call by reference if we want to work it out in C. So in C language, what we have is we had the swap routine like this. A call to the swap routine was made like this, swap AB, and this generated a call to swap IJ. And the values of the variables here, A and B, of the main function were copied into the local variables of the data segment of the swap function. This was I, this was J, and you can have several other local variables. This was copied here and it goes back. And once the call is over, the values are not copied back. Now, in any function call in C, a schematic way of understanding how the functions operate and how the data operates is that for every program there is a static data segment associated with the function itself. That is the code. When you have suppose you are given a function main. Now when it is compiled, it is compiled into two parts. One is called the code segment, which contains the machine code for the program and some locations for certain types of data. And the other part is called the data segment, which contains all the local variables of a particular function, whether it is main or whether it is something else. So there is a code segment and there is a data segment. Now whenever a function is called, the code segment starts executing and a new data segment is created for that function. So let us see slightly in more details how this works. So suppose we have a code segment for a main program and a data segment for the main program. So this is main. And for a function f un, let us say, we have a code segment and a data segment. So this is the code, this is the data, this is the code, this is the data. So in the beginning it will start executing from the main program, and maybe here there is a call to fun. Now as soon as there is a call to fun, so initially when it starts executing in the main program, there is a dynamic data segment which is created. So the data segment of the main program, the variables of the main program which are part of the data segment, for example, say this is fun I and this is a local variable, so this gets loaded into a portion of the memory. Now whenever there is a call to this, a data segment corresponding to this gets stacked up. So this is main, this is fun, gets stacked up here. So this may be fun k. So corresponding to k, there was a block which got loaded up here, and due to the call this value got copied here. And now suppose fun calls another one, say fun2 m, and fun2 is another function which has its own code and data segment. Then whenever there is a call here, this starts executing, and as soon as this starts executing, a data segment corresponding to fun2 gets stacked up at this point. And when this code completes execution, the control returns here to from where it was called, and this starts executing, and this data segment is no longer useful. So this data segment is now, as we can say in stack language, is removed or popped off from this position. And suppose there was another call, say to fun3 m, and there was a third function fun3, then as soon as this call is made after this call, a new data segment for fun3 will start from here, just after fun. So it works like this: when this is called, a data segment is put here. When this calls another one, the data segment of this is put beyond it. When suppose this completes execution and goes back, then this data segment gets popped off, and then if this calls it this one, then again a data segment for fun3 starts from here. So this is a schematic which is very useful in understanding exactly how the program works. A sequence of calls work. So we will keep this schematic structure in mind, and we will see that most of the data which are variables are dynamically allocated in the data segments. For example, they just go on being stacked one after another. However, there are certain types of variables in C which you can declare to be fixed, and they will exist in the code segment. We will come to such examples later on, but this dynamism of the data segment should be understood more clearly, and we shall see some other programs to understand how exactly this works. This will be especially important when we come to recursive programs, when we know that various data segments of the same function may exist in the stack, because the function may be calling itself directly or indirectly. So we will come to such functions in this class, but before we go to that, in C a function can be used like we have used it as a subroutine before in swap, but a function can also return a value. So in C you can make a function return a value and put it on the right hand side of any expression, other than making it like a subroutine call which we did in the example of swap. and we shall see such an example for the computation of GCD before we move on to another more involved example. So let's go back and see. This is a program which computes the GCD of two numbers. This is the main program. It has got three integer declarations in n1, n2 and n3. It reads in n1 and n2 and computes n3 is equal to GCD n1, n2. So now here we have used it as a function which is going to return an integer value, and then we print the value of GCD saying GCD of this and this is this n1, n2, n3. And here we have declared the function GCD. The function GCD takes in two arguments I and j, and we can declare the arguments to be integers inside here. We have seen how to declare it outside the parameter list. We can also declare it here, and we declare the function itself to be an integer, and we compute the GCD by the standard well-known technique of computing GCD. That is, if I is less than j, we exchange I and j so that I is greater than or equal to j, and then we divide I by j and take the remainder. This one finds out the remainder between I and j, and if the remainder is not equal to 0, we continue by making j moving I to j and moving j into the temporary location. The temporary location is the remainder. So this is the standard and well-known technique for computing GCD of two numbers, and here we have used it as a function, and we have used the modulus operation, which is I percentage j, which returns the remainder of division between I and j. So as long as the division is not equal to 0, the remainder does not become 0. Whatever we do is we make the dividend, we make it the divisor, sorry, we make the divisor the dividend, and we make the remainder the divisor and continue. So I hope this is okay, and we'll just execute this. Therefore, the GCD of 45 and 105 is 15. GCD of 99 and 33. GCD of 37 and 53 is 1. So this is a function which returns a value, and you can make this function into returning anything. It can return integer, it can return character, it can return several other things, and we shall see how to declare even complex such returns for a particular function. And in order to make it return something, you have to specifically give this statement return. So we have given the statement return j. It will, therefore, when the function completes execution, the value of j will be returned. Here, just to introduce the while statement. So this is the while statement, and in this while statement is like any other standard while in other programming languages. The loop starts here and continues up to this point, and in that while statement we have just converted the divisor and the remainder and adjusted their values. And the meaning of while is, as long as this condition is true, it will execute. When this condition is false, it will jump out of the loop. So we've seen the for statement for looping, and here is the example of a while statement for looping. There is another statement called the do statement, which we shall come to later on. So we've seen that a function can be used to return values, how to change the values of the parameters, and we've seen how functions can be used to return values themselves, okay, and be used in any expression. Now we shall see a slightly advanced feature of a C language which does not exist in languages like Fortran. And we'll take up the classical example of computing the factorial. All of us know that n factorial is equal to 1 into 2 into 3 into n. And an easy way in which we can write out the factorial program, a program which those who have written in Fortran would have written down always, was something like this. M is equal to 1. Its C equivalent would look like this. This would be the C equivalent for the program. Just in a loop, you multiply 1 into 2, then into 3, then into 4, then into 5. However, factorial has got another interesting inductive definition. And the definition of factorial can be written out inductively like this. Factorial of n is equal to 1 for n equal to 1 and is equal to n into factorial of n minus 1 for n greater than 1. So factorial of n is equal to 1 if n is equal to 1, which is the base of the inductive definition. Otherwise, it is n multiplied by the factorial of n minus 1, which you can obviously see if you look at it backwards. It is n multiplied the factorial of n minus 1. Therefore, we get here an inductive definition. And in many cases of problem solving, we will see that induction is a way of decomposing a problem into many parts. And C language provides you a mechanism for directly working out such an inductive definition. That is, we are able to get an inductive definition if the programming language allows a function to call itself. And we shall see that we can write down such functions directly in C language. So we'll write out a factorial function in C using this idea and see how it executes. So let's go back and see how factorial executes. Yeah. So this is the main program. We have declared two int n and m. We have read in the value of n, and we have called in the main program m is equal to factorial of n, and we have printed that the factorial of n is equal to m. And what have we done in the main program? In the function fact, we have declared a function called int fact, which takes in an integer parameter. We have initialized int to 1. Now look here, we can do an initialization even during declaration. So we are slowly introducing various concepts of C without just learning them one by one. I will just introduce them as and when we continue our programming. So we can initialize a variable like this, but the main part is this. If I is greater than 1, then m is equal to I into fact of I minus 1. So here we have done the calling of a function, and this function calls fact. Fact calls itself, and we return the value of m. So if m is equal to 1, it returns 1. Otherwise, it computes this value. So we have written out a definition of a function which calls itself. Such a function is called a recursive function. So let us first see whether it works. So if we give 1, we get fact 1 is equal to 1. If we give 2, if we give 3, if we give 10, I think 5 is a value which we know. So we do get the factorial value if we write out such a program or a function which calls itself. So such a recursive function which calls itself. Now how does such a function execute? That is the most interesting part. And we will go back to our concept of the data segment stacking one after another, and we will see how it executes. So our basic part of the recursion was fact n, or say fact I, was equal to I into fact of I minus 1. That is if I is greater than 1. Now suppose it is called with a value. So in the main program, suppose you read in the value 3 and you call it with a value of fact 3. So now what happens here? For a data segment for fact is called, and here you have got the variable I which takes in the value 3. Now once you get the value of 3, you again call fact. So another data segment here for I is created with value I minus 1. So you get 2. Now once you get 2, since this is still greater than 1, again you call fact. So another data segment is created with the value of I to be 1. So the data segment, new copies of the data segment continue to be created one after another like this. Now when I is equal to 1, this condition does not hold and you return 1. So once you return 1, you come back here. You come back to this program, and this value, the value of here computes to 1, and so this comes back here and computes 2 into 1, and this value is returned back here, which goes back, and the computation there now returns 2. Now this value goes back here, and 3 into 2 returns 6. So what happens when a program is called is that you have got the fact program which in some place says m is equal to I star fact I minus 1. If I is greater than 1. So whenever this starts executing, say as we said with 3, at this point of time it makes a call to another function. So now we will understand it in a slightly smaller schematic. There is one variable only, which is I, and another variable which is m. So there are two variables in the data segment of fact, I and m. So there is a pointer which waits here and calls it, and it is waiting for the return for the call when I is equal to 3. So here I is equal to 3, and m we had initialized it to 1, so it was just 1. And at this point it calls fact with fact 2. So again two local variables for I and m are created, this with 2, and this, when it starts execution, initializes it to 1, comes here I is 2, and it again calls fact. So another segment of two variables are called I and m. Here I is 1, m is initialized to 1. This condition does not hold true, so it returns this value, and once it returns this value, control goes back to this, and this goes out. Control goes back here, and once control goes back here, immediately this value is returned this value is returned from m, sorry, m was 1, so this value is returned as 1. So now m into 1, m becomes, this is 1, 2 into 1 is computed here and it returns m. So m now becomes 2 and this value is returned back. So control now goes back to this pointer for I equal to 3, which was waiting here, and this now computes 3 into 2 and returns 6. So this will return 6. After making this 6, it will return 6. So this is a way in which you can understand it. We have only had one recursion. We'll have recursion of various types later on. In order to understand such things, it is also useful to just put in some diagnostic statements in your program. For example, I've just in the program, this is the same as the previous program. We read in n, okay, and then m is equal to fact of n, and then we print it. Here, as soon as it enters, I printed in fact inside the factorial program, and I print in the value of I and m, and then we compute this, and after it comes out, again I print in the value of I and m, and we know that m is going to be returned. So if we execute this, we will see exactly the sequence in which calls are made and the values of the variables are occurring. So suppose we put in 3 as we put in previously. Now see what happens. You first go inside the fact routine with I equal to 3, and then you call it with I equal to 2, then you call it with I equal to 1. This one terminates first, it goes back to the call which was made with I equal to 2. This one then terminates and returns 2, and then this one terminates and returns 6, and finally you get your value. And if you put in larger values, you will always be able to see exactly the sequence of calls, and you can print in all the local variables to see what are the values of the variables before the call is made, that is just as you enter the call and just as you go out. So this is the sequence in the factorial program. And finally, the factorial program, if you have understood the factorial program, then you need not write down m is equal to fact n. You can simply put in the function call even in the print statement expression. It works like any other expression, and you can put in the factorial call here. Similarly, you can put in a factorial call here in the return statement also, because a function can take part in an expression. So here what we have done is we have rewritten the factorial routine with I equal to 1, return 1, else return I into fact of I minus 1. So we just put in a recursive function here, which is an expression, and still it can be executed inside the factorial routine. So this is the same as the original factorial function, just that I have introduced the concept that since a function returns a value, it can take part in an expression, and it can take part in expressions like this. So this is how recursive programs work, and we shall see more complex recursive programs in future classes. But before terminating this lecture, I would like to reiterate the fact that recursive programming is a very, very useful thing in problem solving, especially problem decomposition can be done mentally. In a large number of problems, you can mentally decompose the problem into two parts. As we said, even that minimum of n numbers, you can divide it into two parts by splitting the set of numbers that you are supposed to read into, say, two parts, and then recursively solving one part and recursively solving the other part. That is, if you are asked to solve the maximum of n numbers, you can split it up into two parts of n1 and n2 numbers, and then compute recursively the maximum of the first n1 numbers, the maximum of the next n2 numbers, and then find out the larger of the two. So recursive decomposition, inductive principles will be very useful in our study of programming methodology, and it is very nice that advanced programming languages now do support recursive programming. So, and we shall make ample use of such recursive functions while solving more complex problems. We shall also see more of recursion in future classes, but I think today we will stop here.